Hello everybody and welcome to Handmade Hero Show, where we code a complete game live on stream. We did the work yesterday of making sort of a permanent source code file that we generate ourselves, which has sampling spheres in it for sampling our lighting. And the reason we're doing this is because we don't want the burden of producing high quality sampling patterns at runtime, because that would cost too much. So what we want to do instead is build some sampling patterns that we can just use that don't cost us anything, because we just have them stored as raw data arrays and we just use them directly. That's what we want to do. And so we did all the work to do that, but what we haven't done yet is actually put something into that generator that produces nice, like high quality sampling patterns that actually sort of cover the sphere in a nice uniform way. Now, there's a lot of ways we might do this, and we're going to have to talk about those now, but that is our goal for today, is just to take that code we wrote yesterday and augment the part that generates the spheres to, instead of just spewing white noise and normalizing it out to the sphere, what we want to do instead is have some sort of a nice uniform covering of that sphere that's noisy, meaning it's random points, but that they still tend to have a sort of roughly equidistant kind of covering to them, right? So what I'm going to do now is I'm just going to show you what I'm talking about for those people who missed our stream yesterday, and then we're going to talk about some strategies that we can use to try and solve this problem, right? So here goes the build, just making sure everything's built okay. I also should probably note that there was where's our GitHub? I should also note, some people were saying for GCC, we wanted to put our line as, this is just a for Linux compiles. There's a line as movement we want to do, so maybe I'll do that really quick too, just to help those folks out in the sphere generator. This has nothing to do, oops, that's not what I wanted at all. This has nothing to do with what we were going to do today, but it's just a really quick change we can make. So basically what happened is we wanted to make sure that these things were aligned so that in case the compiler generated SSE loads that required alignment, they would be correctly aligned to 16-byte boundaries. This global align as here is the line in question, and what they wanted was just to say, look, global has to come after it or GCC gets really confused. So we'll try just doing that move. We've got two of those. There's one here and there's one here. And assuming they don't cause us any problems, we're just going to leave it like that. Again, that's just to allow people compiling with GCC, which we don't do. But people who try to follow along the series on GCC, just trying to make it so they don't have to make any changes to the code base to compile it, right? That's all we're doing there. Okay, so anyway, if we go ahead and compile and just verify that everything compiles okay, we're not actually running this at the moment, but we can probably add some stuff for that in a minute. If we go to the debugger and we run the debug build of our game, which is a little slower frame rate rise, but when the lighting isn't running, it's still totally usable. That's the main difference. Lighting takes up a heck of a lot of frame time in debug mode. So if I go ahead and take a look here, what you can see is those are all our light probe points we're going to be starting with. These are our purple points. That's what we're trying to get working, is light probing there. And in order to sample, we sort of built this little sphere here that we're just visualizing the lighting directions that we're generating on the sphere. And you can see it kind of hanging on around up here. And what you can see is this is a white noise. And white noise, for those of you who haven't followed the series much and don't know about the colors of noise, white noise is basically pure entropy. It's entropy that is as close as possible to real random events. So something that has no correlation or pattern to it whatsoever. That's what we've done here. We've done as close as we can to white noise on a cube, or inside a cube, I should say. So just generating points inside a cube. And then we pressed those points out to their closest point on the sphere. And that's what we've got here. And that's why you can see it's roughly like pure entropy. Like you can see in here, it just looks like a random clustering of points, some far, some close, right? Which is what you expect from randomness. But you can see that there is some really sparse, obvious places along the faces of the cube. And that's to be expected because there's more area, more volume out. If you look at the difference between a cube and a sphere, there's more area of that, a volume of that cube in the corners, right? That all get smushed down. That whole part gets smushed down to the same general region of the cube. And so even if we were trying to do pure entropy, this isn't a good way to do it, right? And we knew that. We were just trying to put something in there to make sure our whole code path works. So this is kind of roughly what we would expect to see for white noise inside the volume of a cube, then pressed onto a sphere. But that's neither here nor there, because I just wanted to show you it running right now, because we don't want white noise anyway. And so let's talk about the kind of noise we want. We've talked about it before in Handmade Hero. You should all know what blue noise is, but we'll talk about it one more time. Blue noise, also called Poisson noise sometimes. They have slightly different meanings, but for our purposes, they're usually used interchangeably. What's going on? There we go. All right. Sorry about that. All right. So let's just talk about this really quickly on the blackboard. I'll mention the blue noise and what we're trying to accomplish with that. And then we can kind of talk about how we're going to get it, or ways we could get it. So we're going to talk about blue noise slices today. And I'm going to talk about sampling patterns in general a little bit here. And we'll just kind of go over what we might want to do. So like I said, if we are talking about, let's just say, a 2D domain, because that's a little bit easier to describe first, then we could talk about the types of noise that we might be talking about, and we could have blue and white. This we could call, sort of entropy, and this we could call Poisson, perhaps. We could also call this random. Who knows? Depends on how you want to talk about it. But this is not. Right? This is not going to be that. So white noise is the equivalent of literally randomly picking a point. So if I pick some point here, the next point that I pick can literally be anywhere. There are no restrictions on where that point could be. And there's no reason, literally a pure random distribution of points could have 2 points on top of each other. My first and second point could be in the same place in an entropic distribution, right? Why? Because pure chance could someday produce that, right? I may get the exact same point twice. It's possible with pure entropy. What you generally see with pure entropy, right, is just complete, it's just this. It just looks like complete random. There's no pattern to it. You can't find a pattern. Knowing one point or some sequence of points tells you nothing about the point that comes next to it. That next point could be right next to the one you just did. It could be completely off in the other direction. There's no guarantees about it at all. All you could really say about pure entropy is that if you took enough of it, you should see something that, you shouldn't be able to get extraordinarily improbable things like everything clustered right there, right? If you take a big enough random series, you should see a relative coverage of the space with some gradually varying density, right? But you should generally cover everything, because if it's really random, there shouldn't be any bias eventually towards putting everything in one place. But that's it. That's all you really know. You don't really know anything else about it, because it's random, and if you could know something about it, it wasn't random, right? It's unknowable. Might be some way to say it. Now, blue noise, or a Poisson distribution, or depending on how you want to phrase it there's different words for it. When we talk about that distribution, there is something you can know about it. It's still random, meaning you're not supposed to be able to predict what the next point is from any given point in the series in any precise way. But unlike the unknowable pure entropy distribution, a Poisson distribution, or a blue noise distribution, is supposed to contain the property that once a point, any point, is placed into the system, you will not place another point near to that point. So there is some sort of a fundamental distance that usually when we're talking about these blue noise patterns, we care about that distance, and we specify it perhaps. Once we've placed down a point, while I cannot tell you anything else about where I'm going to place my next point, I can tell you it will not be in here. And that goes for the sequence forever. Every time I place a point, that neighborhood around the point is removed permanently, and no future point may land within there. It's not just the next point that can't land within there, it's any point. Now, these sorts of noise have different things that you might care about in terms of audio production or who knows what. But for graphics work, we care about Poisson distributions or blue noise or whatever you want to call it. We care about these for a number of reasons. They come up a lot. And the reason is because there's two different things, both of which are very important to graphics, and both of which really want blue noise. The first one is random distributions of things that are supposed to mimic what happens in the real world, okay? When things are placed in the real world, in reality, they typically don't follow a white noise pattern. And the reason for that is that while there is enough general stochastic randomness entropy in the real world to produce white noise, on top of that white noise, there is typically some constraint that reduces it to blue noise. And let me give you a concrete example because you may be going like, huh, I don't understand. Let's take something like trees. How will trees be placed in the real world? Well, a tree, we get one of them, and it can grow. Someone planted a seed, who knows how it got there? But the first tree grows. That tree produces seeds. Those seeds occur throughout the tree. They will fall onto the ground, and a huge number of factors will control where they fall. They will fall near to the tree, to a certain extent, but then the wind will randomly, we have no idea how the wind is going to blow, but it will blow some of the seeds around. Animals will eat the seeds and poop them out somewhere else. We can get situations where, a bird might grab some of these things and move them. Huge numbers of completely unpredictable things act on these seeds so that probably we would expect within a region around the tree, we would see basically a white noise distribution of these points that is perhaps distributed only with the density function that says that the further away you get from the tree, the less you get. So we would expect a little bit of a knowable thing about our white noise, which is that the density of the noise is centered around the tree and gets less and less as you get further from the tree. But other than that, we have no idea, right? So you might think that if you wanted to know where trees grow, you would say, just pick random points and maybe we'll throw them out with a higher percentage chance as we get further from the tree, right? Does that produce a good estimate of where trees grow? And the answer is no. Why? Because after we distribute the seeds, what determines whether a tree grows has a lot to do with one really big factor. How close is it to an existing tree? An existing tree takes all the sunlight, takes nutrients from the ground, takes all the falling rain, right? And so in order for a new tree to survive, it must be at least some distance away from the existing tree. Now, what happens when that new tree grows? The same pattern of white noise will reoccur, and we continue. What that means is a forest is like a huge blanket of white noise that then had a constraint put on top of it that any two trees too close together aren't going to grow, right? That means that something like blue noise is a really good approximation for what you visually see when you look at a forest. A somewhat random distribution of trees with no two trees being too close together, right? Again, it's not a perfect simulation of it. We're not actually simulating all the things. And in nature, you probably can get certain situations where two trees go very close to each other because the light was just right and this tree kind of bent too far this way because of a storm, right? So if you really wanted to really simulate how trees grow, there's a lot more we could add to that simulation to make it really good, right? But to a first approximation, and certainly one that no one would bat an eyelash at, blue noise is perfect. White noise isn't, because nobody would look at what you generate as a forest. It would see tons of places where there's all these trees clumped together, and then some spaces where there were no trees, and then more clumps, right? It would look really weird, and you'd be like, I don't know, that forest looks weird, right? Whereas blue noise, you'd be like, yeah, that looks roughly like a forest, right? And the same is true for lots of stuff. Flowers in a field, grass on a field, etc., etc. blue noise for distributing the individual plants makes a lot of sense because they compete for resources, right? And so that's one place that we see blue noise, coming up. It's just I want to distribute things, But another place that we see it is where we're talking about it today. So I want to give you that perspective because now you know one place that it comes up. Here's the one that comes up today. What if this has nothing to do with distributing things that have to remember the real world or competition for resources or anything like that? But what if I just have a limited amount of work I can do? I'm limited, right? Because computing power is not infinite. So I'm limited in the amount of work I can do. And I have something, anything, that I need to do that work on, right? I have limited resources and I want to do something to a very large data set, right? And the question is, if I know I can't process everything that I want to process, I can't just do all the work, how might I distribute that work across everything I could do to get a reasonable approximation of the result? And of course, that is what we talk about when we talk about sampling. If I can't afford to do a perfect solution, and I have to just pick a few things to do that will approximate the correct result for anything I might want, for any work, how can I best distribute the locations of that work, right? And so I can give you any number of examples of what I mean by this, but for example, a really simple thing. I want to take an image, really, really dense image, right? It's 50 billion pixels by 50 billion pixels. I can't even load it into memory, it's so big, right? And I want to ask you, what is the average color of this image, right? So I can't even load it into memory, and I quickly, really quickly, I want to get an estimate of what is the average color of the pixels. Now, normally in an image that is anything that we would normally process in computing, a small image, right? 256 by 256, a little tiny sprite. It's hilarious that that's a little tiny sprite when that's the whole size of the screen on like an Apple II or something, but the times they have it changed. A little tiny sprite. What do? I just go through all the pixels in the image, adding them up, and I divide by the total, and I got the average, right? It's easy, no problem. But if now you tell me there are trillions and trillions and trillions and trillions of pixels in this thing, which is what would happen if you had a 50 billion by 50 billion image, because it's 50 billion squared pixels, right? I don't want to wait for that. I don't want to go pay the AWS fee to have all of these cloud machines taking little segments of this image and adding them up. I just want an estimate, right? So the question is, how would you distribute if you know you can only afford to load 50,000 of the pixels and add them together and average them? How would I distribute them throughout the image in order to maximize the chance that I am going to get a good result, a good approximation? Now, those examples are not, that particular example is not as good as it could be in today's day and age when we know there are other constraints involved. So talking about pixels is probably not the right thing to do. You probably want to talk more about blocks of the image that you could load. But either way, I have some finite element of the image I can load, and I know I can't load all of the trillions that there are. How should I distribute them? And the answer for any kind of sampling problem is actually, again, it comes back to the Poisson distribution, the blue noise distribution. Blue noise is the most effective way to turn something where you cannot do all the work, but you want an approximate answer. It's a way to turn a trillion points into a few hundred points and still get a good approximate answer. And you may ask me, why? Why is blue? Why not white noise? Why not random, right? And the answer has to do with the quality of the sampling that you get coming out of these answers, right? if you pick something highly structured. Because let's look at what the alternatives are, right? This was alternative 1, right? And I didn't really give an alternative 2. I just simply said, hey, here's the solution, right? Because we were talking about what we're going to do, and we're going to do this. But there's another alternative, right? This is random. This is structured, right? I could choose to sample things completely regularly, right? In a grid or something, right? So there's two kind of polar opposites. You could say that, you know, there's like a line between completely random and completely not random, right? And structured, completely structured sampling or distribution is like a very regular pattern that has a completely regular structure imposed over the top of it. Whereas a completely entropic pattern like white noise has literally no structure imposed on it. There's nothing you could say about the structure of it. It's completely nuts, right? So if we take a look at these two extremes, why don't we want one of them? Why don't I want purely entropic sampling? Why don't I want purely structured sampling? And the answer is because structured sampling will fall prey to any structure of the image. Let's suppose I have an image that's just a series of stripes, right? And I ask you, what's the average color of the image? Like I said, what's the average? What is it? Well, if I just have a series of stripes, and those stripes happen to be placed at, you know, an interval that doesn't line up with the structuring pattern, with this sampling pattern, I would say the image is just completely black. If this area is black and this area is white, I'd say it's an all black image. There's nothing in it, right? But actually, the average color is actually somewhat bright. It's a gray because there's all these stripes in it. I just missed them all, right? Because my sampling pattern is regular and the image pattern is regular and I missed them all, right? And that's very easy to do with real world images because real world images have structure often, right? So what you see is if you feed any image in with any kind of structure, your sampling pattern will pick up the bias in that structure and go one way, whichever way it is. Either it'll oversample the stripes or undersample the stripes, and you end up with a very inaccurate result. Entropy, on the other hand, right, pure white noise, will never fall prey to that problem. It doesn't matter if you feed it a structure image because you have an equal chance of landing on the stripe as in the black area proportional to the area of those things, which is exactly what you would have wanted. However, because it is purely entropic, it will tend to cluster in some regions and leave open space in other regions. What that means is, again, if there is a different kind of structure to the image, where it's got some areas of brightness, some areas of darkness, the entropic version, the purely entropic version, will fall prey to sampling bias where it oversamples some areas and undersamples other areas, right? So again, it will get a less accurate result because it's concentrating its samples, randomly concentrating them, but concentrating them nonetheless in some areas, and randomly missing other features of the image. So again, it falls prey to image structure even though it itself doesn't have an overt structure to it. Because there is some structure that emerges from the entropy, right? And that's the density is non-uniform. That leaves us with this desire we wish we could have right here in the middle. Can we have something that has just enough structure to ensure that we do not under or oversample any regions of our image, but which does not have so much structure that it falls prey to highly structured images, causing it to over or undersampling something? And the answer is yes, we can, and it is blue noise. Blue noise is precisely that kind of noise, which is evenly distributed across the entire thing, but in no predictable way, right? It gives us the best of both worlds for what we actually want. No structure, we can't say anything about how these points come together, but no variance in distribution. The distribution is uniform, right, across the entire thing. And that's exactly what we want. So that brings us to our sphere today. We are trying to sample the lighting, right, that comes in from the entire world. You know what I'm saying? We have like an entire sphere of light coming from walls, bouncing off of walls, coming from light sources, from the ceiling, from the moon, from the floor that bounces up. An entire sphere of incident light is coming into a point in the world. And our light probe is that point in the world. It wants to look out and see what does the lighting look like. So in order to do this, we need to have some way of sampling that sphere. Now, in a perfect world, we would have some magical computing device that just knows the entire lighting, and somehow it can just figure it out, right? Maybe it's so powerful that it's like the real universe, and our CPU can simulate trillions and trillions of rays coming out from this sphere and cover it so densely that 100% of the light is basically captured perfectly, right? We crank up that sampling so high that no human could ever see the error in it. It's that covered, it's just a solid ball when we draw all the points. You know what I'm saying? If we had that device, we probably wouldn't care. Any sampling's fine, even regular sampling's probably fine, because the contribution of each individual point is so low that even though there is still that structured bias as light moves by it, it will have essentially a regular pattern of kind of bias going through it. The contributions of those things are like 1/1 trillionth of a color value, right? We can't see it. So we don't care about sampling very much at all. We don't care about sampling very much at all when we're overpowered, right? It's why we don't care about sampling very much in a lot of places in Handmade Hero, where we do things to like pixels. Because when we know we have so many of them that the eye just can't really see the error, we're okay. But when it comes to lighting, that's never the case. It's a way too high order problem. There's way too many light rays bouncing around any real world scene to ever count them all. And so we're nowhere near the level of detail that we need to just say it doesn't matter. We're always way under it, and that's where sampling becomes very important. You need to make sure your sampling is at least decent, because otherwise your results are going to be way worse than they could have been, because you're undersampling the problem by such a drastic amount, right? So what I want to do to my sphere is exactly what I wanted to do in my previous example when I talked about how do you actually produce good coverage of, say, a plane for sampling the pixels of an image to average them, like I just gave that example. Well, we're trying to do the exact same thing, really, but just on the surface of a sphere. I want to take a good, uniform covering of my sphere to catch all the incident light, but I don't want it to be structured, because if it's structured, it will fall prey to sort of stair-stepping patterns or stuff like that. As things hit the bias of that sampling pattern, its structure, and play against it. I want to get rid of that, right? And so blue noise is the perfect thing for this. It's the perfect way, if I can figure out some way to do it, if I can figure out some way of sort of covering my sphere with a uniform coverage that's still completely random, so there's no way to predict where those points are, but they are equidistant from each other, or roughly, right? Not equi, but similarly distant from each other. That gives me a good uniform coverage of my sphere without structured sampling artifacts. That's exactly what I want. Okay. So what I need to do that, right, is I need to take, wow, that's a really bad circle. So is that, though. So, I'm going to take my sphere, and I want to try and put points on this sphere, that kind of cover it, but that stay pretty well separated from each other, right? There's sort of a spherical, on the surface of the sphere, there's a circular region sort of on the sphere, and I don't let other points go inside there, right? So once I place one down, I keep that region clear from then on of these other points, right, as I'm placing them. And that's how we were doing it. What I was doing before is we just tuned a constant that was how far we wanted that region to be. we'd place something on the sphere, and we'd make sure that nothing else we place on the sphere would go into that region, right? Now, I don't really want to do it that way, especially because we're offline now and have as much time as we want. We can let this run overnight if we want to. We don't care. It could run all week. As long as it comes up with a good answer at the end of the day, we just get an ini file we can plug into our game, and that's instant, right? We don't pay any more cost for it. So I'm free to do whatever stupid, crappy, algorithm I want. As long as it produces the good result at the end of the day, I'm okay. So I can really consider anything I want here, especially because I know the number of points isn't that high. We're not producing 1,000,000 points on the sphere. We're producing like 1,000 points on the sphere, or 100 points on the sphere. In fact, it's 18 times 4 points on the sphere, right? Times the number of spheres I want. Who knows how many that is? So it's something like that. An n squared, n cubed, even an n cubed, really, right? Algorithm, not that bad. 1,000,000 computations, not that bad. A modern computer has 4, 5, sorry, not 1,000,000 computations, 1,000,000,000, has 4 or 5 billion cycles every second it can do. I'm not concerned about things on the order of 1,000,000,000 operations. So we can use cube routines and with impunity at this order of n, and we know that, yeah, it may take a day to run our thing if it really gets ridiculous, or some, there's like 50 n cubed algorithms happening in there or something. We'd still be okay, right? So we've got a lot of leeway here, and we know that we're not shipping this to an end user, so we don't have to worry about the large S. Okay, so what don't I like about our old method of placing down a point and then saying, hey, Mr. Point, make sure nobody else gets into your region? The thing I don't like about that is the tuning. I don't like the fact that we had to tune that radius. Because again, let's just think of it in the 2D realm, because they're not that different. But think about what that means. If I want to place a good coverage of this thing down, and I know that I need, let's say, 5 points, well, I need to guess, right, like what this distance is that allows 5 points to fit in there, but only those 5. If I picked too low, right, let's say I pick a thing that's grotesquely wrong, well, then I could end up with all my points clustered in one area, and it would still work, right, because I'm not getting too close. You know what I mean? So I have to tune this constant to find out where is the breaking point so that I'm just at the right thing where I can still put 5 points, but I haven't done it so large that it can't place 5 points, but I haven't done it so small that it could cluster them together, right? So I'd rather get rid of the tuning now that we don't care how long this takes to run. And what I'm thinking is, again, maybe like a repulsion scheme would actually be a little bit nicer. So a repulsion scheme just says, look, I know I can just place random points down here and who knows where they go. And then if I say I want them to be roughly equidistant, well, maybe I just do a thing where I take the distance from each point to every other point and add a little bit of like force that tries to push them apart, right? If each of these things has kind of, I don't want to say magnetic repulsion, but if each of the points just repulse the other points and I run a little simulation, they should all sort of naturally settle into positions where they're equidistant from each other roughly, right? I think that should give me more or less uniform coverage of the sphere without any obvious structure to it. I think. And I can't really think of offhand. I should probably, if we really cared, we should probably go read some research papers. There's been a lot of recent research in the past 10 years about generating blue noise patterns. So to be honest, like there might be some ways we can jump sort of right to what the correct tuning constant is, and then it's more efficient to generate these things as like place and step kind of functions. But I think at least without doing a more advanced sort of deep dive into the properties of Poisson noise and stuff like this, I feel like the most straightforward thing we could do is just repulsion. Place random points the number of them that you want. So we say we want 1,000 points or whatever. We place those randomly on the sphere, and then we let them push each other by looking at how far apart they are on the sphere, and we apply sort of a force that falls off in proportion to distance, right? If we run that for a little while, we should see our points settle into locations that are relatively sane and relatively good in terms of covering the sphere. Now, there's one other thing I talked about, which is slicing. And what that is once we have this uniform coverage, we have a separate step, which is the slicing step. Right, which is that once we have a uniform coverage of the sphere that has our entropic properties that we want, so we've got this nice like coverage over here, whatever. This is not very good. You know what I mean. A good equal density but random coverage, right? So something that looks sort of like this. Once we have this, we want to break it up into chunks that are done every frame. So if we have, like we were talking about, 16 times 18 times 4, this is how many samples, right? That's how many samples per frame we're doing on one of these spheres. And then we have 16 frames it's spread out across, basically, right? What we want to do is take this nice uniform distribution that we now have, and we want to break it up into a set of 16 distributions, each of which retains most of the good qualities of the total distribution that we're computing over time. And so I don't really know how we're going to do that. What we might do is like pick a point and then pick the furthest away point and then pick the furthest point from those two and then from those three, right? Until we've picked 18 times 4 points. We remove them from the system and then we do the same process again for each slice. I think that might do it, but I'm not totally sure. So we need to come up with a good slicing regime after we're done. But for now, today, I just want to focus on building the first step of the process that I've explained in detail now, which is how do we produce a nice total blue noise coverage of the sphere, and then we can worry about the slicing as a second step, right? Okay. So if you take a look at what we've got already, we are doing the first step just kind of naturally. This right here is a thing that places points onto the sphere poorly, right? I mean, it's good enough, though. It places a bunch of points onto the sphere completely at random, and then, places them into the cube completely at random, and then just pushes them onto the surface of the sphere. This is a biased distribution. Like I showed you, it's got some holes and some clusters, right? But because we're about to distribute our points using a sort of forcing function to get them equidistant around the sphere, in theory, I'm guessing that initial bias doesn't matter because the points are going to move around now and sort themselves out into a nice distribution. In theory, it shouldn't matter. So I don't think, and I don't know for sure, but I don't think we really have to worry about this particularly much because I don't think it's actually going to matter. I think we can just place these points poorly at first, right? So I'm going to label these steps. So I'm going to call this white noise cube projected to sphere surface, right? So we're going to just do a white noise cube projected out to the sphere surface. This right here is the white noise cube, right? Just completely randomly picking inside the cube. And then this right here is the projection of the surface. Take each one of those vectors, normalize it, right? So done. Now, after we're done with that step, we want to do the next step that I said, which is to try and let these things diffuse. So how do we do that? Well, let's just start by saying, look, we're going to run a number of relaxation steps. So we're going to do like a little simulation, almost like a game would do, where we're going to take a number of steps, and on each step, we're going to move the points a little bit, right? So we're going to say on each step, and let's say we're going to do 1,000 of these steps. I don't know how many we're going to do, but we're just going to do some, right? We don't care. We'll tune this constant. It doesn't matter. We actually might, in the future, not even use the constant. We might just look at how far our points have moved. If our points haven't moved much, then they've converged, right? So this may just be a non-issue eventually, but for now I'm just going to do this as the first step. But we can probably remove this constant as well. So we're going to do a series of steps, and for each step we're going to displace our points. And so the way that we're going to displace our points is I'm going to create a secondary array here that's going to be like our force array. And the force array is literally just another set of v3s that's going to be how much we expect each point to move, right? And so we've got two steps here. The first step computes the force. The second step applies it. So what I'm going to do here is say we've got a dir index. The dir index goes to the total direction count on both cases. In each case, I'm going to take the force here. This should be called forces. So I'm going to take the force in both cases. In this case, I'm going to sum into that force something. In this case, I'm going to apply it. So in this case, this is the more simple part of the process by far. This is just directions. Here are like, direction vectors. Each one of these forces tells us how we're going to push it. So in order to push it forwards, I just have, some force. I guess we don't really need to call it forces. It's a little misleading. Maybe displacements is better, let's say. So we're basically looking at, like, here's a displacement, and we compute those in place, because we don't need to integrate the force or any of that stuff. It's not really physics. It's just a basic displacement. So we have whatever displacement we said was supposed to happen, and so all we're going to do... All right, don't ask me why I just did that. There we go. All we're going to do is take whatever the direction was and apply the displacement, right? So we're just going to say, look, for a particular displacement we want to do, we're going to take whatever the direction was. We're going to add the displacement vector. So this is however much the request was to move this point as computed in this loop we haven't written yet. We move it by that much, and then we want to reproject it to the sphere, right? So we want to then say equals nos, right, dir, like so, right? Now, like I said, maybe we want this loop to be a little bit better. So what I might do is just say, look, what we're going to do is say there's a total displacement distance that we're going to record. And so when we come in here, what I'm going to do is I'm going to take whatever motion was produced, however far I wanted to move this thing. I'm going to do this as sort of a write back step. So I'm going to say, all right, let's take the direction here. Maybe I'll do it this way. Let's take the displacement and the direction. Let's do our update step. So I'm going to take the direction. I'm going to add the displacement to the direction. I'm then going to normalize the direction. And then eventually I'm going to write it back, like so, right? And I'm also, by the way, in that step, going to clear the displacement probably. Because, well, I guess, do we want to do it that way? Yeah, probably. So I'm going to clear this thing down in here. Right? So we start out with displacements of 0, and every time I want to zero the displacement out again so that this thing can fill it up, right? So when I come through here, I take the displacement, I apply it, I reproject onto the sphere to make sure I'm staying on the sphere, because I don't want to have to try and guarantee that with the motion, with the displacements that I want to be sloppier about those displacements. And then what I want to do is, before doing the write back, I want to take the length, right? I might take this as a sum of squares just to keep things easier. But what I'm going to do is say, all right, I've got a squared length here. of the difference between the current direction, whatever it is, and the place that I was going to put it. So this is the total displacement, right? This is like the effective displacement squared, right? And I just want to sum those up. So that'll tell me how far I've moved all of my points. When I add them all together, how far have they moved? And so what I want to do here is say, look, if the total displacement squared ends up being less than some, nominal number, so, that, let's say, or maybe even that. I don't know how much I want to say these things should not be moving, but we have some cutoff threshold. So these things are all moving around, and eventually they stop moving, right? And what we want to do is say, once these things have stopped moving a certain amount, let's say this for now, we'll see what ends up happening. We'll try to tune this. After they stop moving enough, we know that we're pretty much done with how much we need to shake the system out, right? Okay. The last thing I want to do here is exactly what I said before. I just want to clear the displacement so that the next time through, it's summing up a fresh amount. All right, so here comes our n squared, right? Remember I told you we were probably going to be n squared or n cubed in here because we don't want to really do too much with this. So what I want to do here is I want to take all of the things that aren't this particular, like I'm going to call these like the repulsors or whatever. I want to take every point that's not this point, right? So this is our repulsor. I also need this. So I'm going to look up which direction I'm on. I'm going to look up which direction, or rather which direction is repulsing me, right? And I'm going to skip myself. So if dir index is not equal to rep index, right? I don't want to compute the repulsion on myself. Now we could be more efficient here, if we wanted to, certainly, by only considering pairs, because the repulsion is going to be the same between the two pairs. I'm not even going to do that yet, right? I'm going to do the stupidest possible thing. So I'll just say, like, to do so I'm not going to bother with that rather obvious optimization. I'm just going to write it just for one and let the loop take care of it, right? Because again, this is offline, don't care, rather want to keep it simple. That's probably going to be the best plan in the long run. Okay, so we grab the direction, we grab the repulsor. We now know, basically, right? We know what the sort of action line is between these two. If we just say, look, if I subtract, right, or the force line, right? If I take the person who I'm talking about and I subtract the person who's going to be pushing on him, then that's the direction the push would happen, right? It's going to come from the repulsor toward the direction. So direction minus repulsor, okay? And then I can trivially say, maybe I don't really want to consider all the points for repulsion. I just want points that are somewhat close to this one, right? So I want to take that force line, and I want to make sure that it points, let's say, somewhat sideways might be a way to say it, right? So I have a direction. That direction, and let me draw this. I'm visualizing all this into my head as I go, and I realize not everyone is. So let's, for the sake of the beginner, let's go ahead and sort of show explicitly what this is. So let's suppose that I have my sphere, like so, and I'm talking about for a particular direction on the sphere, like this. I'm talking about some other direction on the sphere is going to push on it, right? It's pushing on it. And the idea is it's going to push it away. And it's probably going to push it more strongly the closer it is, maybe or maybe not. We'll have to see how we want to do that. But what we definitely know is once something is like more than like half a sphere away, like if it was all the way over here, I don't probably want it to push anymore. I only want things to push if they're in like the same hemisphere, let's say. And anything that's further away than that on the other side of the sphere, I don't want to use. Well, if I already know that I've got two normals, the repulsor is already a normal and the direction is already a normal. If I just dot product those together, I form, the standard dot product here, right? So I've got A and B. If I take the dot product of A and B, I know that that equals 0 precisely at 90 degrees, right? As I go behind it, it becomes negative. As I'm in front of it, I come positive. So I can pretty clearly do a quick clip in here where I say, hey, if dir.rep there is less than 0, I don't want it. So I'm going to restrict my force computations to only things that are positive dot product. So those two things are less than 90 degrees. 89.99999 degrees is okay, but 90 is not. I want everything to be less than 90 degrees apart if they're going to be applying forces towards each other, right? Now, if I literally wrote this right here, if that was what I left in there, we kind of have a system that may be a little ill-behaved. And why might it be a little ill-behaved? Because now I've got forces, who knows what I'm going to write in here for force computation, but I've got a hard clip, right? And if in math land, right, this is Mr. Function, right? Maybe this is the force of repulsion, right? And this is the distance or something. There's some function I'm about to write that's how hard this thing pushes this other thing away, right? If I insert an if is just a hard clip, right? It will say, look, as soon as I get to this one point, we no longer use that function and we drop straight down to 0, right? That means as I'm running this, as people come in and out of that hard clip, they get the force or not, right? And it could cause jitter and just bad behavior. What I'd much rather have is a smooth fall off. And hey, I just wrote one, right? I literally have the smooth fall off sitting in my code and I chose not to use it, right? So no, keep that in there. We've got that inner product. Let's use that as part of our fall off. So here we'll just say, look, if the fall off is greater than 0, use it. If it's less than 0, don't. So that way we come down, nice fall off, and then we stop, we clip right where we already knew we were at 0, so that if doesn't cause a discontinuous change in our force amount, it only causes a discontinuous change potentially in the derivative, but we don't care so much about that, right? Convergence properties and all that stuff is kind of out of the scope of what we're talking about here, but you can see why in general you want sort of smoother fall off curves so that your system isn't dealing with forces that turn on and turn off, turn on, turn off, right? It helps if they kind of fall off to 0, because then there's always a smooth continuous force that it's finding. And these turn into like hard edges in search spaces, and we could go on for a long time about how you search through space for solutions and stuff, but that's getting into really advanced territory that I don't think we want to go. So let's just keep it simple and say, for reasons you can sort of intuit at least a little bit, you don't want your forces turning on and off randomly like that, because the thing that's trying to converge these points is having to deal with these like real surprises all the time. Something that smoothly goes down produces a more gradual like rest into place, which is kind of what we hope these things will do, right? So we're going to come up with a fall off that's going to be based on the inner product between these two. If the inner product is positive, we keep it. If it's negative, we don't. So that means points don't suck, like they won't turn the polarity and start sucking each other in, right? We're just not going to deal with that. We could. Maybe it would be better. Who knows? Because it's still continuous either way. So maybe that would be better, but we're just not going to do that. Points aren't going to pull. They're only going to push. All right, so once we know that we're going to push, we're going to take our force line like this. And I think what we would say is the force line, again, we want to apply that displacement based probably on this fall off. So if 2 points were right on top of each other, right, we would want the maximum fall off. Unfortunately, if 2 points are actually right on top of each other, they can't tell which way to separate. We could try to break that tie, but let's just hope other points would break that tie for them. But in any other case where we produce that line, the line is automatically going to be longer based on the distance, right? So effectively just adding just the line in might be enough, but I think we may want to double up on that by effectively multiplying that by that inner product. So as you get down to here, right, again, because as the line gets longer, the push would get stronger. In fact, you know what? Now I think about it, that's the opposite of what we want, right? We want the opposite of that. So we do want to take this, and we want to normalize that, I think. We want to take the distance between the direction, and we want to, I think, get rid of that length. And then we want to reintroduce the length as being the opposite way. The further you get, the less repulsion there is. Again, this gives us exactly that fall off. So we just need the force line to be the direction, right? And then we'll reintroduce that amount. Okay, so then what we want to do is say, all right, the displacement for this point is now going to get added in this force line times the fall off, right? Times some constant that is our, maximum displacement, basically, right? So we have some idea of what's the maximum displacement per step we want to see. And so on a sphere, we don't want these things jumping wildly. We know the sphere has radius 1. We probably don't want anything moving more than like, a tenth of a unit. Because that's a pretty big move inside something that's only, a sphere that's got a radius of 1. So it's 2 units across in diameter. We don't want something moving, anywhere close to 1 whole unit there, because that's just too much motion per step. We're trying to do this gradually, right? So maybe that's the maximum, and if you're right next to each other, you can move that much away from each other. Because again, remember, this will be effectively doubled in a sense. If 2 points are right next to each other, they'll each move away from each other at that speed. So in effect, you could double it, right? So the max displacement per step wants to probably be pretty low. And it might even want to be lower than this. We'll see. Because that might move too far. In fact, I might set it to something quite a bit lower for now. Just so that we kind of more gradually move it. And now we've kind of done what we wanted to do. At this point, we've gotten to a place where I think, let's put it this way. Let's put this min total displacement per step is like maybe this, right? Meaning if nobody is moving at least that much, then we're kind of done. Right? All right, and so last things last. We've got to break out of the loop at some point, but I think then we're good to go. So we sum up our total displacement. We see whether or not everyone's more or less stopped moving. If they have, we're good to go. And that should, in theory, happen when we get enough people kind of bounced throughout the sphere. Again, it may have to be, this tolerance may be too high. It may be that, or too low. So we're going to have to tune our movement a little bit. There may be a better way to do that, and I'm not sure what it actually is. So I'll tell you what, I think there is a better way to do that. I think there is. I'm going to change my mind on that. So what I'm going to do here is I'm going to say, all right, this condition's actually going to happen here before we take the step. And what we're going to do here is we're going to recognize that we're already doing an n squared loop. While we do that n squared loop, let's sum up the distances. Let's take all the distances from everybody to everybody else, and let's see what they are, right? So for any given point, we will look at what the distance is between that point and all other points as like an average. Is that really what I want? I'm not sure if that's really what I want. You know. So the goal of this distribution is to ensure minimum distance between points, right? So what I actually want to do is I just want to find what's the closest point. So for every direction, what I want to do is find what is the closest point distance, right? So this is the thing I actually want to find, and I can find it squared because I don't even need to take any square roots in here. So when we come through here, what I'm going to do is say, all right, we're going to get the force line that we're going to compute here, right? And this force line I'm going to compute like this, and then I'm going to do the force line length. Right? Like this. And then I'm going to say if force line length is, oops, if I spell it correctly, is greater than 0, we're going to do this, right? So I'm basically going to normalize the force line attribute, but I'm going to remember what that force line length was. I'm then going to say if the closest distance squared, right? Oh, and I guess since I have to do this, I don't even need to do squared. Now I think about it, because I had to do the square root anyway to normalize the vector, so it doesn't matter. So if the closest point distance, right, is greater than the force line length, then I know I've found a new closest point, right? So now I know what the closest point distance is for each one of these, for every point, right? And so what I'm going to do here is on every time through the loop, I'm going to say the min closest point distance equals F32 max, and the max closest point distance equals F32 min, meaning I'm going to start them on the opposite ends spectrum. And each time through the loop, I'm going to just track what they were, right? So when the minimum closest point distance gets updated, it's going to become the minimum of itself and the closest point distance for this point. And the same will be true of the maximum just the other way around, right? So exiting the loop, I now know for all of the points in the system, I know the smallest, like the closest any two points are, and I know the furthest that any 2 points are, right? I know those two numbers. And so now what I can do is I can say, let's get to the point where our minimum closest point distance and our maximum closest point distance, excuse me. Do I want to say converge or just not change? That's a tough one. So I guess I want to say so what I want is I want the minimum close distance to stop improving, right? I mean, that's sort of what I want. And so if the previous minimum closest distance didn't get any better, right? So, you know, if you imagine this. I essentially want to say, look, if the last minimum closest point distance, like if I didn't get any better, do you know what I'm saying? You know what? I can't put this down here though. I just realized. Well, I don't know. So if the last minimum closest point distance didn't get any better, like if I actually, am not really converging. So if the last minimum, if the absolute value between these is like starting to be less than our epsilon value would be, something like this. So if we really can't spread these points out any better, so if the absolute value of the last minimum closest point distance minus the minimum closest point distance, if it hasn't improved, right? Then we're kind of done. And I don't really know. Really, I guess we want this to be directional even, right? If the last minimum closest point distance minus the minimum closest point distance, if this hasn't gotten bigger, right? Meaning if this number is like going up, that's just bad, right? Because it should always be going down, right? The last minimum closest point distance should have been higher. I guess that would do it. I don't know. We're gonna have to. This is gonna be the interesting part of this, I think, probably. So that's what we kind of want to do here, and we don't really know what this is going to do because we just spewed a bunch of code into it, and we haven't thought too hard about the numerical conditions of it. So who knows? But wait, where's my? I don't know why that wasn't in the recent list there. There it is. All right. So if I step into this, I'm going to take a look at this code and see what happens here. Here's me calling, generate lighting pattern. Set the breakpoint on that function. So when I come through here, what we're going to do is we're going to look at this loop. We're going to go through our directions here, and we're going to compute this minimum closest point distance. Let's just step through this a little bit once just to see what's going on. So here's us with a direction and a repulsor. Here's the direction, here's the repulsor, right? They're two different points in the world. They're fairly well spread apart, actually. We happen to have a fall-off value that is positive, although probably not super positive. No, it is, actually. Is that right? Should it be that positive? Oh, yeah, okay. Yeah, actually, they are somewhat close together. Compute the force line, look at the length. We normalize the force line, so now our force line should be, a normal-looking thing, and it sort of is. We then take our max diff step, and we supply our displacement. That displacement, by the way, should be zeros. Now we should get something in there, and we do. It should be a small displacement. We look to see about the closest point distance, and we update that. That should be set to basically float max. By the way, I think this is a nice feature of, I don't know if you noticed this. I actually asked George to add this, and he did, and it's awesome. If something happens to be exactly float max, or one of those other constants, it shows you. How cool is that, right? So you don't have to look at this and wonder if it's quite float max. You just know it's float max. And so that's really, really nice feature. I love that feature. I don't know if George, I don't know if you're with us today, but that's a great, I've loved it. It's been great because I often set things to the maximum values like that. And it's nice to see them shown exactly as a human readable value, so you don't have to guess. So in here, when we do our closest point updating, we're gonna, as we go through, we're gonna kind of look and see if we track which one is closest. Hopefully we do. Eventually, we're gonna update our min-max closest point. Let's see if that looks at all reasonable. So min closest point distance, max closest point distance. Looks like float min didn't maybe work there. Unless our float min is wrong, which it might be. I'm not sure. Oh, you know what? That's not in the C thing, is it? Negative float min. It might be. I don't know. George, help us. Anyway, here where we get maybe I set that constant wrong. I don't even know. But anyway, here's our min closest point. There's our max closest point. I'm looking at the wrong place. I'm like, why are they the same? That's why they're the same. So here's the thing that's furthest away, and here's the thing that's closest. It looks like our check is wrong here. Oh, yeah, because that's going the wrong way. I set that wrong, didn't I? Because that number is supposed to be getting larger. So no wonder I was like, why did it exit so soon? This should take a while. So this should actually be 0, right? Because you're moving things further apart over time, or you're trying to, right? So this is more what I would have expected it to take a long time to run. And now the question is, let's see what we're getting on each individual step, right? So you can kind of see it's slowly getting larger, right? Slowly, slowly, slowly as we go. Let's let it run for a while. And so what it looks like to me is it looks like our displacement step is maybe not as big as it should be, because I feel like we should be able to converge a little faster than that. Also, our maximum displacement step might want to be proportional to those min distances. So I feel like this may want to get adjusted, right? So like if you look at the last min closest point distance, we may want to start subtracting that away from our step or something like that. At the moment, I'm going to crank that up a little bit so that points can move more, and just see what that does to our convergence. So that, it looks like at that point, the next step moves things a little too far. So I do think what we want to do is make this max disp per step. I do think we want that to kind of be conditioned on the current state of affairs, if you will. That leads me to go, maybe I'm going to introduce a little more n squaredness here, because, hey, 2 n squared steps, it's not that different than 1 n squared step in terms of whether or not this thing can run. So maybe what I'll do is say, look, what if we said first, we're going to take in fact, oh, you know what? We don't have to do that. So the max disc per step is just multiplied by displacement. We can just sum without knowing it, right? Because it's just a scalar that affects the total distance moved. So what we can do here is say, look, let's move this down and say, let's put it in here. Let's take the max displacement per step. We'll take it into this equation here, where we do our displacement. We'll multiply it here. We don't care how much they moved anymore. I don't think I care about that total displacement. So we're just going to get rid of that. I'm going to get rid of all of this, right? So I don't care about that. We write them back. So all I want to do now is say, let's condition the motion, whatever movement we're going to do. Let's condition that on our new minimum. So whatever the minimum closest distance is, I don't want to move, when two people are close together, or, we could actually use the maximum. I don't want to move however far apart the two furthest people are. I don't want to move anyone more than a certain amount of that distance, let's say, right? So, maybe we do something more like this. So when things are far apart, we can move them maybe 1/10 of that distance at a time. When things are not, we slow it down, right? And maybe this needs to be a higher, maybe that needs to be more like 1/4 of the distance. I don't know. But that way, at least it's based on something we measure. And let's see how that goes. All right. I want to watch the convergence too myself. So here we go. So here's our min closest point distance. And you can see it kind of converging there towards, well, it kind of oscillated a little bit. I feel like that was too ungentle. maybe, does it need to be on the min closest point distance? The problem is that could be effectively nothing. That's a hard one. I feel like we're still not picking the right way of doing it. Like, this is much better, right? You can see that converging really good. It kind of started off with big movements, and now it's getting smaller movements to try and dial that in. And I think that's exactly what we wanted to see. And so I think, again, like, the problem here is I'm not quite... I'm going to go draw down the blackboard, I think, because I feel like we can get this pretty good, right? Still working on that sort of endpoint there. Oh, wait, is there a new version of Remedy, by the way? I just glanced over the chat and I saw that. Oh, darn, man, there's an 8.1. What's an 8.1? I don't even know. All right, so this eventually converged, which is what we want. So we now know that this sort of works, right? And we need to improve our convergence, I think. But we can talk about that as a separate part. Let's first see if this produced any good results. We could have tons of bugs in there, so it could have been converging on total garbage, right? We watched it do a nice convergence on something, but who knows if we were measuring that something correctly. So I believe that wrote it out to the Handmade sphere. Yeah, here's our Handmade sphere. If we look in it, it generated some sphere, right, for us. Who knows if it's good, but there it is. So if I go ahead and copy the Handmade sphere.inl to w handmade code handmade, what is it, like sphere sampling or sampling spheres? If I go ahead and copy that into the actual game, right, I should now be able to go run the game. Oh, and I want autosave turned on. Autosave is pretty cool, by the way. It just saves things automatically for you, so you can just kind of like hop around and you don't have to think about it anymore. So I'm going to go ahead to win32handmade.rdbg. I'm going to compile it like so, so that we've got our new spheres in there. And then I'm going to try to run it. Now, if I go look at those points up here, I don't know what I'll see. That looks like the same set of points. What am I missing? There's no way that produced the exact same set of points, I don't think. I mean, but that looks pretty close. Did I not rebuild that properly? Pretty sure I did that right. Maybe we've got some pretty nasty bugs in here. I don't know. We should have seen something change, right? It seems unlikely that we produced exactly the same thing. At least it seems unlikely to me. Let me take a quick gander. So the fact that I didn't see an exclamation point and this didn't change. So what happened? Did my copy not work? Did I screw something up? because this is not the right, it didn't update the file. Let me, maybe 4Coder saved it or something. Let's just find out. There we go. That's the right one now, right? Okay. So now let's see what our sphere looks like, because I guess, I don't know what I did wrong there, but I did something wrong there, because it didn't seem to update the file. Now maybe that's a totally separate issue, but here's the actual sphere, I guess. Still looks wrong. Like, it doesn't really look like they fanned out as much as they should to me, right? It's a little hard to see because we're seeing all the sides of the sphere at once, but you can see that those are not blue noise by any stretch of the imagination. Those two are way closer than those. So that just does not look correct to me at all, right? And this is clearly the new one, I think, right? So we're definitely rebuilding with the correct sphere file. Well, so much for a quick victory. I guess we've got some issues here that we've got to look at. So what's the deal? How did that not really push our stuff around very much, would be my first question. So taking a look at what we're doing here, let's see. You know what we probably would like to be able to draw this out, you know? It would be nice to be able to see it happen over time, which maybe we need to do in order to actually debug it. So if I can't get this working relatively soon, I may just move it into the game and have it be a thing we can run every frame and watch. But if I look at what's happening in here right at the moment and we take a look and see what the displacement steps are and so on. So let me just make sure I'm not doing anything too stupid. So if we look at the displacements, I grab those out here. I take whichever direction I'm currently on. I'm going to write that displacement step. To be honest, I guess I didn't really need to zero those, because I actually sum them up just in place. So I think I might get rid of that as a thing so that it's not in there anymore. As an additional factor. So all I really need to do here is actually say, look, at the end of this, you have to write this back. Into the displacement array that's going to get applied. But when you start out here, it's just going to be 0. So you start out with no displacement, you sum the displacement here, and then you apply, just record it at the end, and that's the end of it, right? So anyway, for each individual point, I'm going through all the other points in the system. I'm ignoring the point itself. And then once I know that it's not the same point, I look up the point, so I have both the one I'm talking about and the one that's going to push me. I look at what their fall off is relative to each other by taking the inner product, because I know they're both normalized. The fall off has to be greater than 0, so they have to be in the same hemisphere. And when they are, I then look at what's the direction that I would push this guy to push it away. And I apply that amount, I apply the fall off based force along that line. So I normalize the force line first and then push it. Now granted, I could do better. I could take the perpendicular in the same direction, right? If we wanted to. And just to give some perspective on that, what I mean there is just that if you look at what's going to happen on a great arc, so, you know, on the sphere, you know, I've got somebody here and somebody's pushing them who's over here. This arc in between them, right? So I look at that arc from the side. I have somebody pushing here and somebody pushing here, right? The line between the two of these is not actually the direction along the sphere I would push. It has an outward component. And what that means is the amount that I push it, some of it gets eaten up by the renormalization. Because if you look at what happens, right, if I were to travel around the sphere, I would be going this way. But I'm actually pushing it this way, and that renormalization causes me to move less than I normally would, right? And I move less proportional to how far away I am. So one might argue, perhaps, that we're over damping by using both this fall off and the renormalization step. But that doesn't explain why we don't seem to get any real separation. That's just a tuning issue, and it probably wouldn't account for everything, I don't think, right? Okay, so we sum up all of the displacements here, and then we come through this part of the code, and we have a termination criteria. We know that we're not terminating particularly early because we watched it run several iterations. On each iteration, we load up the displacement in question. We no longer need this. We could just do this because we don't clear it. So we load up the displacement that we're going to use. We take the direction part here. We're going to update that. We don't need this, right? So we're just doing that. We apply whatever the displacement is that we asked for, so like so, times whatever the size of displacements we're going to do. So these displacements here are a sum of displacements, and the max of each of them that each of them could have been was this amount. So we're just multiplying that using the distributive property, knowing that a sum of things that can each be this long itself could just be multiplied by a unit displacement summed together. So that's what we've got. Then we renormalize to project the direction back onto the sphere, and we write it back into the location in the array that it came from, and that's it, right? Now to me that seems pretty simple, and then from there we just pluck those out like this into our samples, right? Without really doing anything else to them. And so that to me suggests that we should be seeing a pretty good distribution here in theory. Now, there are other errors we could have, right? We don't know for certain that our output is being correctly, like we do a weird little casting thing to get around the fact that C++ was horrible and was screwing us. So I don't know offhand that we actually have the exact right thing happening in terms of transporting our results over to the saved side of the system, and so it is a little bit hard to know, to be fair, exactly what's going on there. But what I would like to do is let's just take a quick look, let's do like a sanity check, if you will, on H8 Sphere, and I'm going to go ahead and just go full banana cakes here and say I'm going to write out the actual file. I think it's handmade sampling spheres, right? Yeah. So when we run this thing in the debugger, it will actually just overwrite the file, right? Full up. So if I go ahead and do a dir w handmade code handmade sampling spheres, and I just do a del on that, if I run it now, after it finishes with the apparently really crappy repulsion steps that I've written that don't work, it will write them out to that file, and this will just verify that we're actually writing to the thing that we then compile and use, which I just want to make sure is the case, because if we're testing it by looking at it visually, I want to know that I'm actually, getting that result. And so in here, I'm going to go ahead and also I'm going to kill that buffer. So the spheres aren't loaded at all, and off we're going to go. I should also add a little printf to H8 Sphere. In fact, while this is running, I might add that. So, like when we go in here and we're going to do another round, I might just say, let's print out something like this, or like generating points. And then I might do like this. where we just look at the difference between these two things. And I'll put this down at the end here. So maybe I'll put this at the top. So basically what's going to happen is I'm going to print out in here like what the min closest point distance was and what the max closest point distance was, and then the max minus the min. Because we really want those things to be getting closer together, right? Okay, so this ran, and now if I do a dir on that, you should see it's there, and it is, right? So if I run this, right, here's where we can kind of see those differences, right? And you can see them supposedly converging, right? This is the difference between the biggest distance between any 2 points and the smallest distance between any 2 points. That's not the, sorry. It's the biggest and smallest distance to the closest point, right? And you want those things to get very close together. And, you know, they are really close together. So I don't really understand why we're not getting a better result out of this, but I don't know. So another thing we could do here, let me see about actually looking at that as the value. So if instead of looking at the last min, right, if instead I just look at this convergence here, right, and actually I guess I still do want one of these, but instead of last min closest point distance, I want to look at last min max separation. And so I want that value to get very small. And so in here, if I said, all right, let's just do this, where we compute the min-max separation, and that's just the max closest point distance minus the min closest point distance, right? Then at each step, I want the min-max separation to have gone down, right? So I want to say whatever the last min-max separation was, minus the new one, I want to have taken a positive improvement step. So the last one should be higher than the new one. And so if for some reason it's not, if it gets like down to the point where it's if it's like too small of an improvement, then we bail, right? Something like this. And so we're just looking for an improvement each time through the loop. Oops. Yeah. And it looks like maybe I've got that a little bit backwards there. So let's just take a look here. All right. So we've got our min-max separation is the closest point minus, like the farthest away closest point versus the, right? So the separation here, is going to be tracked over time. So the next separation, it's actually got worse, which I suppose could happen. That's why we exit. Is that really right? That means our min closest point distance got more than our max. Gosh, I don't really know. Yeah, we're gonna have to study this a little bit a little bit harder. So let's suppose I did a different one. Let's suppose I did this. So it'll run for a long time, and we just watch what happens. I just want to see what happens. So here are those numbers, and you can see that they do seem to be kind of converging. So I guess it must just be the first step is a little too large and causes a general displacement. I don't know why that is not a real number though. What did I screw up there? Oh, there we go. All right. So, with the exception of the first time where we print out garbage, obviously, because of that, you can see the improvement here. It just gets lower and lower each individual time, right? And then it starts going up. Weird. Kind of oscillating in that general region. But you can see that according to our metrics, we are still like, we're still supposedly getting better, right? And now we're getting worse. Like this number is now going up. So I think we're going to have to do a better job here. Sort of the crappy thing that I pooped out is not good enough. And we're going to have to figure out like how to actually repulse these things in a way that's going to be more stable. Again, I'm not really sure what the actual problem is, and we're going to have to analyze it and find out what, because otherwise we're just kind of like going blind there. And if we look at the maximum closest point distance, and we're kind of using that as a guide to how much we allow things to repulse. Yeah, I don't really know. I don't really know what we want to do with respect to that. I do wonder if we want this thing to just only use the cosine as the fall off, and we want to push them. We want to kind of rotate things more so, like make sure that their displacement direction is more based on where they actually are. And we could do that pretty easily because with just a few cross products, you can see how that would work. For example, if I wanted to do a tangential push, right? So I want to push this along the tangent. It's not that hard. If I have, this vector and I say I want to push it that direction, but what I really want to do is push it along the sphere in that direction. Well, I know this direction because that is just this direction. It's the actual thing I'm pushing. And so if I took this direction and the push that I want, and I take the cross product, right? You can see what that's going to do. It's going to create a vector coming out the side of those two, right? And then if I recross, right? If I then recross, I will get the tangent that is along that same line, right? So if I cross the force line, if I do force line cross direction, right, this way, I get a thing that comes out here. And then if I do direction cross that product, I get something that comes out here, right? So what I could do is something more like this. So again, just right-hand rule, crossing the force line itself with the direction. That gives me one thing. Then I cross the direction again with the force line. That gives me the push direction, right? And then I can proceed as normal. I just normalize that thing, and off we go. That's not the problem, almost certainly. We've got other issues. But point being, I can do something like that. And, you know, who knows, right? It certainly has an effect on the system. That one thinks it converged, right? But who knows what that means? I mean, you know, like I said, it looks like we got bugs, so we'll focus on this next weekend and get that worked out. But using the tangential push, let's see if we resulted in any kind of a different actual result, because I don't know what that looks like since we can't see it when it's running there. So here's our sphere. And again, this is so creepy. Like, it looks exactly the same. I'm kind of wondering if there isn't a bug separate from this that has nothing to do with here. What I want to know, I want to see if I kind of want to see if our like if the compiler is doing some alignment casting issues, because we had to do some weird stuff, right, with C++ to get this to work at all. And so I want to see if this thing is actually causing a problem here. You know what I'm saying to you? I don't see how it could be, because everything's still on the sphere. So I don't think that could really be the case, but I'm pretty weirded out by this. Because I don't see how we're doing so much moving of things around and not anything that's not getting better. And maybe there's an obvious reason for why that would be, but I don't know what it actually is, right? Maybe I'm just measuring the wrong thing. I don't know. I'm curious now, too. Can we get down to another level of precision now that I'm pushing along the other one there? Oh. That's not the program I was trying to run. There we go. So this one can get pretty low, it seems. So something is up, right? I mean, it just doesn't make sense. We've just got some obvious bugs in here that we can find. But this is supposed to measure the difference between the 2 points that are furthest and the 2 points that are closest. Not 2 points that are furthest, but for each point, right, it's saying for every point, what's the closest point to me? And I'm looking for the highest and lowest of those values. And this is claiming that the set of points that the thing is outputting has almost no difference. So every point is equidistant, roughly, from its closest point. I mean, maybe you got to measure more points than that to get an actual fair output. Maybe. But, like, it sure seems like we're not getting that distribution. I mean, in other words, when I go and run, so let's say I run the program, that means I shouldn't be able to see any 2 points that are obviously closer together than any other 2 points, right? The closest point to every point should be about the same distance away. You know what I mean? Trying me get this into... I need a way to quickly center. I need a button for like center around the weird sphere thing I made. It takes too long to get it into position. So, I mean, just looking at it, it's obviously not true, right? So look at this point, and you can see the closest points are there or there, right? There's nothing closer to it. And yet you come up here, and those 2 points are like right next to each other. So it's obvious that even our measurement is wrong. So the question is, how is our measurement wrong? If I look here and I take this direction, and I'm looking at all of the other points in the system, I think, right? Unless there's just a bug in that, just full stop. When we, unless I'm not outputting all my points, but anyway, when we look here at these, so I guess I'm not looking at ones on the other side of the hemisphere, but that shouldn't matter, right? Because your closest point isn't going to be on the other side of the hemisphere. So when we look at this, we take the subtraction of those two, right? Oh, that's the problem. This has to be done right here, right? So the only reason this thing was getting better was because we were fussing with it in the middle of this probably, right? So the forced line length here, when we actually take it, it has to be taken here. That wasn't the problem before though, because we were still doing that. So I don't know, that this doesn't really explain the bug. This is just, we introduced a bug sort of in here, if that makes sense. So this forced line length has to be taken here basically. And this has to be a NOS, right? So but again, doesn't really help us. So I just don't understand. Yeah, I just don't understand what's going on there. So that fixes that with respect to sort of the tangent push, but I don't suspect that will help us at all because we were wrong. It was working correctly the way it used to be, and now it's gonna. I don't know if it'll be able to converge with the force line push or not, but even if it does or doesn't. We don't have any explanation for what we were seeing before, right? So looking at this, it's having a hard time really getting down particularly low, which kind of suggests to me that maybe we've got issues with how our convergence is working. Like maybe one of the constants is bad or something like this. Let's just take a quick look. So if we take a look down here, you know, maybe this is too large. So let's take small steps. See what happens. And so this number continues to climb, which is sort of what we want. So we just want this number to always be going up. And then this number will do whatever this number does. And eventually, hopefully, this will catch up to it as this number stabilizes, right? And you can see that with a smaller step, it looks like before we were maybe taking too large of steps and we were overstepping things, because you can see this appears to be converging much more cleanly, right? And so, you know, it's kind of it's a monotonically improving system now by the things we're measuring. Now, I'm expecting it to still not be any good, because I'm expecting if we go, because like those spheres just look completely ridiculous when we looked at them. They didn't even look like what we were measuring made any sense. So I'm not expecting this to actually fix the problem, but at least now what we're looking at in terms of convergence, looks proper, right? You can see these two things moving towards each other, and they just constantly move towards each other over time, right? And so now, if we looked at this value, I would expect to be able to see this converge after the first few iterations where we kind of get things more going in the right direction. Eventually, we should see this number start to go down to something too low to be worth it. And that would be kind of the end of the convergence, right? And the question is just how low can this get? And I don't know. So let's take a look at what we can tune this constant to just to see if there's anything more sensible. And then we maybe have to think about how to actually compute that constant in some way that isn't ad hoc, right? So again, let's just take a look. Now we're moving at, before we were moving at a tenth of a step, a 100th, I guess. And now we're moving at a quarter instead of a tenth of a tenth. So, 0.025. And looking at that, again, still looks like it's kind of going properly. So the min distance is monotonically increasing. The number up here is kind of just doing whatever it's doing. But this number continues to climb. And this number should, in theory, stop climbing at some point. In theory, right? Because we want things to always be getting further apart. So we want this number to kind of go up. And then this number should stop going up at some point. So again, that all looks kind of good. I'm going to keep pushing it and just see if I can sort of manually root find to find the amount of repulsion that tends to work for this system. And then I think we really want to maybe do a better job and try to figure out how to actually compute that number, or figure out what it should be for a given system so that we don't have to tune a magic constant. Because again, we want to be able to change the number of sample points and still have it work. And I think if we tune a magic constant, it'll probably be sensitive to the number of sample points. So we probably want to figure out a way to compute that, even if we have to take, maybe we have to take into account the number of sample points, but we still want to be able to do that, right? So again, still looks pretty good, right? And you can see it sort of, this number is constantly going down, and this number is constantly going up, which is what we want. Yeah, so like, what the level of convergence is that we can actually expect in this case, I'm not sure. And again, that's why I say we kind of want to solve these numbers. We want to go look at these numbers and actually do a better job analyzing them so we know what to set things to and what to look for our termination criteria, rather than just I'm intuitively looking. So now we're in a situation where we've definitely gotten ourselves a little bit screwed. You can see this number was oscillating a little bit, so it's kind of going up and down. Which means this number doesn't continue to improve, right? So it's really hard to say, like, yeah, what we want to do. I almost want to plot this. So anyway, I guess what I would say is I'm going to use 0.02 as the cutoff for now. We're just going to see what happens if we write it out at that. And that's something to which it seemed to converge relatively quickly. And I just want to see like what it writes out at that point, right? And it's not going to be great, but I'm just interested to see. So what it would appear like happens is now when we go to run this thing, I've compiled it. Oops. I always fat finger that. You know, ideally we'd see a nice sphere. We're not gonna. We're gonna see the same exact sphere we always see. And so I guess, yeah, we're gonna have to put some structured art in here and figure out what's going on, because I have no idea. But like, you look at these and it's just like, it's nothing like what we're actually getting, I don't think, on the readout, right? So if we look at that readout, the readout would have had us believe, right? I mean, like, let's recall what that's actually printing here. So when we were looking at that number that's 0.02, that means that if you took the closest point to any given point, the two furthest ones and the two closest ones differ by only 0.02, right? Where the sphere radius is 1. So 2/100ths of the sphere radius is the difference, right? Hundredths. Between the furthest away, right? So if we were to look at like somebody who's out in the middle of nowhere here, let's say this saucy gentleman right here, this one. The closest point to that guy is like there. And the argument is that the difference between that distance, right, and say that distance is 2/100ths of this length. It's just nonsensical, right? It doesn't work. So we know we've got a bug, like a bug, not an algorithmic bug. An algorithmic bug would be like if this was reporting numbers that were looked about congruent to that, then we would expect what we get, what we're seeing. But we're not seeing that. What we're seeing is things that are massively further apart than our algorithm thinks they are. And that means we're just doing something fundamentally stupid. We just don't know what it is, right? So we're measuring something wrong, or we're writing out the values wrong somehow, which doesn't make any sense because they wouldn't be on the sphere, presumably, right? So something's really busted, but we don't know what. Probably like this stuff here somehow, or something, like the way that when we're taking this closest point distance, right? So, you know, I don't know, somehow this thing, we're taking the closest point distance, and then when we remember the minimum and the maximum of it, somehow we're just I don't know. I mean, that looks like that's right. So I just don't know. I don't know how we're managing to get such a laughably wrong number when it looks pretty correct. It's almost like we're just not using this, right? Like it's not actually somehow using the output. But since there's only one array, I'm not sure how that's possible, right? Like, I'm not sure how it could be doing anything else. So I don't know. So we'll go to a Q&A briefly, but we've got our work cut out for us because there's something nasty going on in there. And maybe over the week, those of you who want to try your hand at debugging can try debugging this yourself and see if you can find it. Oh, did I type it wrong? Oh. All right, so as usual, the chat spots my typos before I do. That's a pretty bad typo. Okay, good. So now you can see this number here is oscillating a lot more wildly than it was before. And we're not getting a good monotonic descent at all there, right? But I gotta be honest, even so, we're still in a little bit of a bad predicament because that's not that much of a displacement, to be completely honest with you. But it's still enough, right? Yeah, so let me try setting our convergence, our maximum displacement down a little bit now that we have a better measurement here. And let's see. If we can get anything resembling convergence on this, right? All right, let me go to the Q&A while that saucy gentleman is running. When will you start read chat during session? Never. The rule of the show is I may not take hints from the chat while the show is going. So because we want the chat to be interactive at the end of the show, I can't really avoid spoilers, right? But the point is when I actually, when I'm actually doing the programming on stream, I'm not supposed to be getting any help because we're supposed to see what I do, right? So I don't get, it's, because that's unfair, right? It's like having a bunch of extra programmers finding bugs for me, and the point of the show is to show what happens when a regular programmer is working on stuff, you know, someone with a lot of experience, but you're supposed to see me make mistakes, and you're not supposed to see me get outside help, right? You're supposed to see what I have to do. So no, never is the answer. I will never, I'll never read the chat during the stream because we're supposed to get at least 2 hours of me trying to do my best without hints. Because obviously if you have more eyes on the problem, you get better, right? The more people there are looking at it, the better you'll do. You know, especially since some people watch this show are themselves very experienced programmers. If you have a lot of experienced programmers watching, you can find a lot of bugs because those people all bring all their experience with it too, right? So. So looking at this convergence, right, it looks a lot better, but it looks like it's never going to get too much below like an 0.035. We can look to see what that actually looks like. But again, I'm not expecting this to actually fix the problem, to be honest. So... Could you use a function like gravity and just sum up all the forces applied by all the other points where the force is proportional to the distance squared? That's exactly what we're doing. That's exactly what we're doing. Like literally, it's just gravity. We don't, at the moment, quite use distance squared. We use a cosine fall off rather than distance squared, but they're, you know, pretty similar, so... I don't know, like maybe this thing is now too low and should actually be set a little bit more aggressively. Just looking at it, looks like it is still kind of doing a pretty good job reducing that total number. But but it would remove the if statements. I mean, you're never going to get rid of all the if statements, right? Because even gravity, if two things are directly on top of each other, gravity doesn't have a solution for that, right? Because you don't want to apply the distance squared as the force. You want the inverse of the distance squared. And so when the distance approaches 0, you get a singularity. So you've still got the if. Is something like a golden spiral method too deterministic? Yes and no. If you forget this particular episode because we're doing something specific here. If you go back to the original episodes when I was doing the hemispherical sampling, you can see us talk about various methods. And what we determined roughly was that you really do want blue noise. There are other sampling patterns as well, and people have done some sampling patterns that are supposedly like brand new ones actually that came out in just the last few months where people are like, hey, I think we found a way to do blue noise sampling on hemispheres with a structured pattern that's actually about as good. You can use something like that. Right, you can, if you want to. Is there a save load state of the entire game for resume purposes, like serialization? Not at the moment. We don't do that. No. We will add something like that for the shipping version for sure, because you'll want to. While we probably won't allow you to save your game because it's sort of a roguelike kind of thing, we will presumably allow you to quit the game in the middle of a run and then restart and be in the middle of the run again. Looks like our separation's getting worse right now, even though our minimum distance is continuing to climb. So we may be kind of hitting the threshold. Hard to say. Like, it might end up going back down again. As long as the second number, as long as this number here, right, continues to climb, we're still getting better in a sense. But the problem is this number is also climbing. That's why this number was not going down. But now we've gotten to a point where this number is going down again, so who knows, right? Let's see. How do you measure stalls that happen on a particular memory load? Oh, man. I mean, I want to say you can't really do exactly what you're saying, meaning there is no real way to say, tell me the exact number of times that I had a cache miss on this particular memory stall. And the reason for that is kind of like a Heisenberg thing, because you actually could measure that, but by actually looking at the difference between the two performance counters right around the load, you would probably change the actual number, right? So it's pretty hard to do exactly what you're talking about, but a version of what you're talking about is not impossible. So if you just want to know, generally speaking, between 2 points in your code, how many times did you stall on memory, you can do that. They're called the performance counters. They're inside all of, like you look at an Intel chip. If you go look at the documentation for it, it documents a bunch of program counters. And what those programmer counters are is they're effectively things that you arm. You can only have a couple of them active at any one time. I think it's like 4 active at a time, I want to say, although it might be more than that. But anyway, you can only arm a certain number of them at a time. But basically what you do is you say, I have 4 counters I can activate at any given time. Which 4 do I want? And you can say, I want number of L1 cache misses, number of L2 cache misses, number of L3 cache misses, and number of cycles stalled in the scheduler waiting on a cache fill or something, right? There's a whole bunch of these, right? And what you can do is you can arm those counters, run some amount of code, hopefully a large amount, and then look at them at the end. And then you tweak the code, run it again, and look at the difference. So you can do a thing that helps you start to eliminate memory stalls by arming those things, right? And when you arm those things and look at their differences, you can start to make improvements to the code. Does that make sense? So there are things you can do. It's not as fine-grained as you might want. But again, by structuring that, or like another way to do it would be like vtune, for example, tries to use like stochastic methods to do some attribution of like, oh, this was the instruction pointer at the time when this kind of thing stalled or whatever. You know what I mean? So you can do things like what you're asking. You just can't do it exactly because modern CPUs are so intricate that if you actually tried to measure just the behavior of just that one line exactly, right, you would affect the behavior just by the act of measuring it. That's just the nature of the beast, I'm afraid. I only caught the end of maybe saying, won't the points get farther and farther from the sphere since you only normalize the end? No, we normalize every time through the loop. So you're correct. That's exactly what would happen. The sphere would just expand forever. But what we do is every time we update, we project back down to the sphere. So we force them to stay on the sphere as they move each step. But you're absolutely right. If we were doing that only at the very end of all the iterations, that's exactly what happened. They just get further and further from the sphere. What spatial partitioning method would we use on this problem? It's a bit premature for me to really say because we haven't profiled it, so we don't know what's taking most of the time on each individual step. So I wouldn't really want to recommend anything without knowing what's actually slow, right? We would have to think about how we would want to cluster our points, but we could probably just do a pretty rough and tumble clustering based on, some kind of directional buckets, or something. But again, I don't want to speculate because unless we've actually sat down and gone, what do we need to speed up? It's pretty hard for us to guess what the correct spatial partition would be, right? Okay, this is kind of out of left field. For a dedicated server using WinSockets, how would you send the player data? Is like a JSON serialization possible, or should I use other formats to send player game state to all clients like every X ticks? So what I would say is serializing to something like JSON doesn't make a whole lot of sense for a real-time transmission situation. The reason for that is twofold. One is that JSON is way larger than it needs to be. And so when you're talking about something like a server, your goal is to try to minimize the amount of bandwidth that server is using. And so you certainly don't want to bloat all your data out by turning it into structured text first, right? Something like JSON may be perfectly reasonable for using for debugging or for just getting the thing working if you want to be able to inspect what the things look like. Maybe you send JSON at first just to get it working. But you really don't want to stick with something like JSON because you're massively increasing the amount of bandwidth for no real benefit, right? Nobody benefits from having it be JSON. So once you're going to send stuff over the net and you're talking about a performance-oriented scenario such as a game server where you want to minimize bandwidth because you're paying for that bandwidth, or somebody is, what you want to do is figure out how to make the data as small as possible. And so what that usually boils down to is sending it in binary and probably sending it some way that is actually delta compressed off of existing data. So typically what you want to do is you want to look at what the last ACK was you received from a client and see what they know about the world. And when you go to send them something else, you say, what's the minimum set of changes I would need to send to them in order for them to understand the new state of the game now, right? But that's usually what you're doing. So no, JSON, not a great idea. It may work for games that are very simple and don't have a lot of players, don't have a lot of entities, don't have a lot going on, right? But for real-time 30 or 60 frame per second games trying to update their servers at close to that, a lot of game servers run undersampled because they're crappy and poorly written. But when you're trying to accomplish that, you want to minimize the amount of text that's flying around, and you want to keep your packets binary, clean, tight, and hopefully diffed so that you can send the minimum amount of information and send it as often as possible, right? That's usually what you want. Converging to the situation where the closest point, max and indices are similar, isn't that something like trying to produce a regular solid polygon within faces and then rotate it by arbitrary angles? It's something like that, but it's not exactly like that because remember, we do want this to be noisy, and so we want there to be we want it to be irregular, and that would be regular, right? So it's not entirely different, but it's not really what we want. It's slightly different because of that structure that it has. By the way, is this thing almost converged down to the amount we actually are looking for? No, not quite. It's like it's only barely there. I'm gonna try this and see if we can run one that we can actually see what it looks like. I'm guessing we've still got other bugs though. Maybe we run this and it's just great, but I'm guessing we've got some bugs, and so I'm gonna try it. But I'm guessing that even after we do this, it's just not going to be sufficient, right? That's just not. It's not in. It's not in the realm of possibility, right? I think that's it for questions. No more questions? Probably. On a shipping game, would you hardcode the shader into the game or have it in the asset file? That decision would probably be made based on a couple factors that probably aren't going to help you, and I apologize. But I would say it depends on the engine and the development process. First of all, if there's only a few shaders, I wouldn't bother putting in the asset file because it just adds a load dependency that doesn't really need to be there. If there's hundreds of shaders, then they probably belong in the asset file, but that depends a lot on the development process. If I have a way to do like some metaprogramming where I just write my shaders in my code base and it automatically like hot loads them during development but can bind them directly into the code at runtime or something, blah, 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 then I might not want them in the asset file, right? Because I generally don't want them in the asset file. They're not assets, really. They're core engine features that kind of need to be there. So I would say it really depends, but I would skew away from asset file depending on what I actually have to work with. Do you have projects that are voxel octree based? Not at the moment. Not really, no. Let's see. Another possible invitation would be starting with a regular polygon distribution, then apply an initial random displacement force and continue simulating. Yes, that would probably be one way to do it. So it looks like we finished, by the way. So we should be able to build and run here. So you can see it's the exact same sphere, right? Basically. So I'm pretty sure we've got some bugs in just the way we're like writing and reading this, or something is happening, because there's no way we can really be measuring the distances the way that we say we are. If they were actually getting measured correctly, we would not be able to see a sphere that looks like this. So we just have some bugs, some other bug, right? And we just want to Oh, and no, we don't have the buffer open. The buffer's not open in 4red at the moment, by the way. So we just have some other bugs here. I don't know what they are, but we gotta look at them and figure out what's going on there. You know, I don't know whether it has to do with how we're drawing them or what's going on there, right? But we're probably just straight up like doing something stupid, like not drawing the stuff that we actually saved out, or who the heck knows, right? If we look at where we're actually drawing them, you can see us doing it here. We go through the sampling spheres one by one in theory, and then we go through the bundles and we load them out, right? And you know, it looks okay. You know, it all looks well enough, so you know, I don't see any obvious bugs in here, certainly. So it's hard to say. You know, there's a lot of places that bugs could be lurking in here, though, because, for example, when we look at this, one question here is, what, when we look up at that, are we actually seeing, you know, 1,000 points? And so one way we could maybe like also debug this a little bit more is by saying, well, you know, if we were to change the total number, so like in here, right, when we look at H8 sphere, if we were to say, like, what if we just only did 1? Then we would expect 18 times 4 points, right? And so who knows, like, what exactly that'll give us here, but like as we sort of push our things around, you can see them kind of oscillating wildly. This is why I say our constants need to get tuned a lot better, because they're you know, they're not convergent. In fact, they don't even make sense. I mean, you look at what's happening here, and like supposedly our repulsive force is making things get closer together, right? Which just doesn't make a lot of sense at all. So you know, something about what's going on here is just kind of busted. But we can reduce the number of points, and then we should be able to get some kind of situation that, yeah, I don't know. One question I guess I do have here is also like, you know, does this just end up oscillating around some minimum that it actually is finding, you know? And I don't know the answer to that question either, because we're not really looking at it too much. This should probably draw some stuff as well, right? But that's sort of a separate issue. So, you know, you look at that and you're like, well, that doesn't look particularly good, right? And if I twist the constant there to make it so that that can converge, I think it's literally that bad, right? What's this? And so if we look at what that displayed there, we should now, just as a sanity check, if I rebuild, I should see only those, you know, 18 times 4 points on the screen, and they should be placed poorly, right? So there they are, right? And like, so right there I can tell we've got a bug, right? Which is good. I'm glad I did this. So if you count the number that are there, let's do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But there shouldn't be 18. Should there? There should be 18 times 4. So if you look at how this is running right here, when it's outputting these things, either we're outputting the same point multiple times, so meaning either this code is incorrectly writing out the same point every time. And it doesn't look like it is, because it looks like we're doing, 1, 2, 3, right? 1, 2, 3, 1, 2, 3, right? So it looks like it's certainly writing out them separate, but who knows? And so the question is, like, what's going on in here? Is this wrong? This is doing this comp index thing where it calls get component on a particular one of these. Is that busted? I don't know. Let's find out. So if I come in here and look at what happens with one of these, it sure doesn't look wrong to me, but we know that we know this number. We know this number is 18. And so the question is, if we're drawing 4 of these, why are we only... if we're drawing 4 times for every one of 18, then, where's my 72 points? Why aren't they there? And so as we go through here, something is busted about some aspect of this. And I'm not sure what it is, right? I don't know why we're seeing that duplication. So one thing we maybe should do is just step in here real quick, take a look at what's happening there. So if I go to Handmade Lighting here, and we jump down to this piece of the code, like, what's up? So here I am in this routine. I've got sphere index, I've got point index. And so when we look at the particular sphere we pulled out, we've got the sample directions here, and that's what we're going to be accessing. If we look at one of these, right, sample directions, what we should see, there's our x, y, z, is each of these x, y's, and z's should have 4 elements, and the 4 elements should actually be different, and they're not. So that's pretty much all we need to know. We're duplicating things 4 times for some reason, right? So that's problem 1. Since I'm pretty sure that's not happening in the head end, what I'm guessing is that we're losing those points possibly in the pullout stage. So here's what I'm wondering. It may be that the C++ rules don't require this to actually step each time because of undefined behavior or some nonsense like this, right? So maybe let's say we do this. You know what I'm saying? Now C++ can't screw us, being the incredibly crappy, universally complete garbage language that it is. Now it has limited ability to ruin everything like it always does. And so the question is, assuming there's no bug in here, which I don't think there is, that may have been the problem, right? So let's see if that helps at all. Don't know if it will, but we can certainly try. Also, I think this doesn't actually need to do this if it's just picking it out this way. Like, directions, this could just move to the outside. In fact, this should have been ×4 as well, though. So that looks like a different problem too, right? So I think let's fix both of these. I think we just had bugs in the readout, right? We start with directions. Each time through, we pull out 4 of them, and off we go. That may have been it. Honestly, scary as that sounds. No, 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 no. No. Want to actually rerun the sphere generator here. No. There we go. So I'm just going to rebuild with that, newly built sphere set there. And then I want to hopefully stop at the same breakpoint and just verify that we actually wrote out different values this time. So here's the sample direction, looking at the X, the Y, and the Z, and all of these should now have separate values in here. And hey, now they do, right? So now I should, instead of seeing 18 points, I should see my 72 points. And that may have been the entirety of the bug. Like that could have been it, right? So now if we look at these, hey, that's a pretty regular looking sphere, isn't it? Right? So now let's crank it back up to what we were doing before. Again, we still need to solve this directional problem. I don't want to be sitting around doing this garbage, right? So this is a big to-do here. Determine what the real convergence criteria is. And that's going to take some mathing on our part. So we're going to have to do that. Because we don't want to have to... That value I don't want to have to set as a magic constant. We certainly could, but I'd rather, since we haven't really done anything like this on Handmade Hero before, I'd rather show how you go through working on that part of the process at some point. But if I change it back to 16 spheres now and run it again, here's us like doing that convergence. And let's see if our algorithm actually is pretty good. And it was just our read and write that was scrappy. I'm assuming we don't have any more questions. No, C++ wasn't right. C++ just screws us all the time. It's just a bad language. It creates all kinds of bad bugs that really had no reason to be there, right? It's like, yeah, C++ is like the ultimate bad language. It's extremely error prone. It has lots of really stupid things you can do that allow the compiler to generate garbage and things that are not intuitive based on what you've written, but at the same time, not offering almost any features, right? It has almost no features. They're all really terrible and very underpowered compared to the versions that exist in other languages that did them better, right? So it's kind of like C++ is like the ultimate in crap. But to be fair, one of the bugs was ours. It was the fact that we didn't stride by the right amount. So we had two bugs, actually. One was ours and one was C++'s. Maybe you can convince John to make arguments evaluate left to right in JAI. I don't care what order they evaluate in. I just want them to not do something stupid. Like if you have 4 pluses, that shouldn't all just be able to be represented by 1 plus, which is what was happening there as far as I could tell, right? Like the number of times I increment something should happen in an order, right? And I'm pretty sure in C++, the plus operator doesn't have to do that. Right? I want to say. Don't quote me on that, but that's what I want to say. So this converges to a pretty tight tolerance here. So when we go look at this sphere, I'm expecting it should look very nicely covered. Will I be in the Jai closed beta? I don't know. You should ask John. But if he wants, we can definitely play around with it on Handmade Hero a bunch. Like we could do a few streams where I try to learn it, right? And then people can watch and learn it along with me. And we can write down like any feedback we have or whatever. I'd totally be up for that if it helps. I mean, we could take some of our utilities, like our PNG processor or our font render or whatever, and just re-implement them in JAI and just see how, you know, how it goes. All right, so let's see how our sphere is now. I'm recompiling with the new sphere INL. Beautiful. So our algorithm was pretty good, as it turns out. Look at that. Look at how lovely. Look at that. We did a great job, actually. Well, that's not true. Our convergence is crappy, and our constant is fixed, so we didn't do a great job. We did a decent job. We just had a bug in terms of how we were writing them out. Look at that. That's lovely. Right? Quite nice. And so our next goal is just to slice this, and that won't be too hard, is just to slice this into pieces so that we can have 1/16 of the sphere sampled on each time. And then we can just roll that in as our sampling sphere, and we're good to go. So we're pretty close. We just have to come up with a good algorithm for slicing it, right? Again, that could be just a pretty simple n-squared algorithm that takes like furthest points or something. I'm not sure if that would work well, but that's roughly what we want to do. So I'll be back here next weekend and we'll do that. Until then, let's just appreciate how lovely our sphere looks right now, because it really does look pretty darn lovely. Like, no part of it's really that regular, right? But it all is still pretty uniformly covered. Like, everything is just a little jittered, but it still kind of always has a nice density pretty much everywhere. So it seems pretty good, but I don't know. Who knows? All right. As you decrease the magic number, does this method converge towards a uniform distribution? Nah. Probably. It would probably, if you set the number too low and force it, you probably would eventually get some kind of irregular pattern, because if you don't leave any slop, it can't be completely random. So we don't want it to converge to like to too tight of a tolerance, right? All right. Gonna wrap it up. Pretty happy with that sphere, though. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series at home, you can always pre-order the game at handmadehero.org. It comes with the source code, so hey, you can try your own sphere point generator and see how you do. I'll be back here next week when we'll work on tuning those constants and figuring out exactly how we want to do the repulsion stuff, just to tune that a little bit more, and then we'll do the slicing. And then I think we're good to go for actually using these spheres as our sampling spheres, which is great. And that's another piece of our lighting puzzle solved. That's it for today. Hope to see you back here next week. Till then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.